The grinding sound of metal being torn apart echoed across the battlefield as Lieutenant Ming Zhao ducked behind the burning hull of what had once been a Japanese Type 97 Chiha tank. Blood streaked down his face from a shrapnel wound on his forehead, but his eyes remained fixed on the scene unfolding before him. It was August 12, 1945, in the rugged mountains of Manchuria, and the Soviet invasion had caught the Japanese Kwantung Army by surprise. Through the smoke and chaos, Zhao could see the massive silhouette of a Soviet tank crushing a Japanese armored vehicle beneath its treads, the metal folding like paper as the Japanese crew scrambled desperately to escape. "Collect every piece you can find," Zhao shouted to the small team of men behind him. "We need intact transmission components and armor plates." His orders seemed absurd amidst the carnage of battle, but Lieutenant Zhao was no ordinary soldier. A trained metallurgical engineer educated at Beijing University before the war, he now led the Nationalist Chinese Army's Special Technical Intelligence Unit, a team tasked with understanding why Japanese armor consistently failed against Soviet and American tanks. As shell fragments rained down around them, Zhao and his men crawled forward to the nearest destroyed Japanese tank. Its hull split open like a crushed insect, exposing its mechanical innards to the harsh light of day. What Lieutenant Zhao couldn't know as he collected those twisted metal fragments on that blood-soaked battlefield was that his analysis would soon reveal a shocking truth, one that would explain how material science had doomed the Japanese Empire's armored forces from the very beginning. More critically, by comparing these failures to salvaged German Tiger tank components, Zhao would uncover a technological gap that had sealed the fate of Axis armor in the Pacific Theater before the first shot was ever fired. No one in the Kwantung Army knew that one man's scientific curiosity that morning would rewrite the engineering history of the Second World War. Ming Zhao was born on April 2, 1917, in a small village outside Nanjing to a family with a proud tradition of craftsmanship. His father, a respected blacksmith, had instilled in him an almost religious reverence for the properties of metal. "Understand the soul of the steel," his father would say as young Zhao watched him work the forge, "and you will understand why some blades bend and others break." These early lessons sparked a fascination that would ultimately shape the course of Zhao's life and, unknowingly, influence the technical analysis of the Pacific War. By 1935, Zhao had distinguished himself as a brilliant student at Beijing University's newly established Department of Metallurgical Engineering. His professors quickly recognized his exceptional ability to analyze metal fatigue patterns and microstructures. While most of his peers focused on theoretical studies, Zhao spent countless hours in the laboratory, examining failed mechanical components from various industrial accidents. "Metal speaks a language of its own," he wrote in his journal, "and every crack, every fracture tells a story about the forces that caused it." When the Japanese invasion of China intensified in 1937, Zhao's academic pursuits were interrupted by the brutal reality of war. Rather than fleeing inland with many of his fellow students, he volunteered his expertise to the beleaguered Chinese army. Initially assigned to an ordnance repair facility in Wuhan, Zhao quickly made himself indispensable by improving the heat treatment processes for repairing damaged weapons. His innovative techniques extended the service life of artillery pieces by nearly 40%, earning him recognition from the high command. By 1940, as the nationalist forces struggled to hold territory against the technologically superior Japanese army, Zhao received an unexpected assignment. General Bai Chongxi, the brilliant tactician leading China's southwestern defense, had recognized that understanding enemy equipment was as important as knowing enemy tactics. He established a small technical intelligence unit and personally selected Zhao to lead its metallurgical division. "Oh, your country needs your science more than it needs another rifle in the field," the general told him during their brief meeting in Chongqing. Zhao's team initially consisted of just 4 men, 2 former engineering students and 2 skilled machinists who had worked in Shanghai's industrial sector before the war. Their equipment was rudimentary compared to what Zhao had used at university, but their mission was clear: examine captured or destroyed Japanese vehicles and weapons to identify vulnerabilities that could be exploited. The team operated from a converted textile factory, its machines repurposed for metalworking and analysis. Their first major breakthrough came after the Battle of Changsha in 1941. Among the Japanese equipment abandoned during their retreat were two damaged Type 95 Heigo light tanks. Working through nights illuminated only by kerosene lamps, Zhao's team methodically disassembled the vehicles, cataloguing and testing each component. What they discovered was unexpected. The armor plate, though appropriately hardened on the surface, showed inconsistent carbon distribution throughout its thickness, making it brittle when struck by high-velocity projectiles. The Japanese have sacrificed structural integrity for production speed, Zhao reported. This insight allowed Chinese forces to modify their anti-tank tactics, aiming for specific vulnerability points where the armor was most likely to catastrophically fail rather than merely dent. The success rate of Chinese anti-tank teams increased dramatically in subsequent engagements, saving countless lives and precious equipment. As the Pacific War expanded following Pearl Harbor, Zhao's reputation grew. By early 1944, his technical intelligence unit had expanded to 20 specialists, operating with the blessing of both Chinese and American commanders. It was during this period that fate delivered into his hands the opportunity that would define his legacy: the recovered transmission components from a German Tiger tank that had been captured by Soviet forces and shared with Allied technical experts. Little did Zhao know that these components would soon provide the key to understanding Japan's greatest technological failure of the war. The harsh winter of 1942 had seen the tide of battle turn decisively against the Axis powers. On the Eastern Front, the German Sixth Army was being systematically destroyed at Stalingrad, while in North Africa, Rommel's once invincible Afrika Korps was in full retreat. For Adolf Hitler, these reversals demanded technological solutions, and he had placed his faith in a new generation of heavy tanks, most prominently the Tiger I, to restore Germany's battlefield dominance. The Tiger I represented the pinnacle of German armored engineering at that time, weighing 57 tons, armed with the lethal 88mm KWK-36 gun, and protected by armor up to 100 mm thick. It was designed to outmatch any Allied tank it encountered. The very first Tiger tanks entered service in August 1942, with the 502nd Heavy Tank Battalion deploying to the Eastern Front, while the 501st Heavy Tank Battalion was sent to Tunisia. Across the world, Imperial Japan was also engaged in a desperate struggle. After the initial success of their lightning campaigns across the Pacific, Japanese forces now faced the growing industrial might of the United States. The Imperial Japanese Army, which had relied on light and medium tanks like the Type 95 Heigo and Type 97 Chaiha for infantry support, was encountering American M4 Sherman tanks that outclassed them in every aspect. Unlike Germany, however, Japan failed to develop effective heavy tanks to counter this threat. The divergent armored warfare experiences of the two Axis powers stemmed from fundamentally different strategic situations. Germany fought on the open plains of Europe and the deserts of North Africa, where tank versus tank combat was decisive. Japan, meanwhile, fought primarily in jungles, mountains and islands, where traditional armored warfare played a smaller role. Nevertheless, Japanese planners recognized their tank deficit and sought to address it. In early 1943, under the terms of the Tripartite Pact, Germany agreed to share certain military technologies with Japan. Among these was technical documentation for the Tiger I tank, including detailed specifications of its Maybach HL-230 engine and Maybach Olvar hydraulically controlled semi-automatic pre-selector gearbox. Japanese engineers studied these documents eagerly, hoping to apply German expertise to their own tank development programs. However, the transfer of information was complicated by the vast distances involved. With Allied naval forces controlling much of the world's oceans, physical delivery of technical materials between Germany and Japan became increasingly difficult. Some technical documents traveled by submarine, others by specially equipped long-range aircraft flying dangerous routes over Soviet territory. In some cases, technical information was transmitted through diplomatic channels via neutral countries. One such technical package, containing detailed engineering drawings of the Tiger's transmission system, arrived at the Imperial Japanese Army Technical Bureau in Tokyo in June 1943. Colonel Murata Hisashi, Chief of Tank Development, immediately assembled a team to analyze the German designs and determine which elements could be adapted for Japanese use. What the Japanese engineers discovered, however, was sobering. The manufacturing precision required for the Tiger's complex transmission far exceeded Japan's industrial capabilities at that time. The challenge was not merely one of design, but of materials and manufacturing processes. The Tiger's transmission required special alloy steels containing precise amounts of molybdenum, chromium, and nickel, materials that were increasingly scarce in the resource-poor Japanese home islands. Moreover, the gears required precision machining to tolerances that few Japanese factories could achieve consistently. Nevertheless, the Japanese army pushed forward with plans to incorporate elements of German design into their next generation of tanks. The Type 5 Chi-Ri, intended to be Japan's answer to the American M4 Sherman, began development in early 1944. It would never enter mass production. As American strategic bombing intensified, Japan's already stretched industrial base began to collapse. Priority shifted to aircraft and naval vessel production, leaving tank development starved for resources. By early 1945, the Pacific War had reached Japan's doorstep. On the Asian mainland, the Imperial Japanese Army still fielded substantial forces, particularly the once elite Kwantung Army in Manchuria. Originally Japan's strongest formation, it had been progressively stripped of its best units and equipment to feed the meat grinder of Pacific Island battles. When the Soviet Union finally declared war on Japan on August 8, 1945, the stage was set for one of history's most lopsided military campaigns and for Lieutenant Ming Zhao's most important discovery. The summer heat beat down mercilessly as Lieutenant Zhao crouched beside the twisted hulk of a Japanese Type 97 Chi-Ha tank. Soviet artillery continued to pound Japanese positions in the distance, but here, in this small ravine near Mukden, a temporary calm had settled. Zhao's technical intelligence team worked with practiced efficiency, photographing the destroyed vehicle from multiple angles before beginning the systematic disassembly process. "Sir, you should see this," called Sergeant Wu, the team's most experienced machinist. He had managed to extract part of the tank's transmission and was holding up a gear that had sheared clean across its teeth. Zhao took the component and examined it carefully, noting the crystalline pattern at the breakpoint. "Brittle fracture," he muttered, turning the gear to catch the sunlight. The metal wasn't properly tempered. He placed the gear in a specially marked container for later laboratory analysis. This was the team's fourth recovered Japanese tank that day, and the pattern of failures was becoming increasingly evident. The Soviet offensive into Manchuria had begun just 3 days earlier, but already the once feared Kwantung Army was in full retreat. Their tanks, once considered adequate against Chinese forces, were being systematically destroyed by Soviet T-34 medium tanks and IS-2 heavy tanks. The Japanese armor simply couldn't withstand the high-velocity rounds from Soviet guns, and their own weapons lacked the penetrating power to threaten the Soviet vehicles. What made this particular battlefield investigation unique was the presence of something extraordinary: components from a captured German Tiger tank that had been transported to Manchuria for technical evaluation. The Tiger had never reached Japanese engineers intact. Allied bombing had destroyed the workshop where it was being studied. Now, amidst the chaos of the Soviet offensive, Zhao had the unprecedented opportunity to compare German and Japanese tank components side by side. "Set up the field laboratory here," Zhao ordered, pointing to a sheltered area beneath an overhanging rock. "I want preliminary hardness tests on both sets of transmission gears before sunset." His men quickly established their portable testing equipment, a simple but effective setup that included a Brinell hardness tester, a small metallurgical microscope, and basic chemical analysis tools. As the day progressed, Zhao's team recovered components from 7 Japanese tanks and a substantial portion of the German Tiger's transmission system. Working methodically despite the sound of distant battle, they conducted their initial tests, with Zhao personally examining the microstructure of key components using their field microscope. The differences were stark and immediately apparent. The German transmission gears showed consistent hardness readings and a fine-grained structure throughout, indicating precise control of the carburizing and heat treatment processes. The Japanese gears, in contrast, displayed wildly varying hardness levels, even within the same component, and showed signs of improper heat treatment, resulting in a coarse grain structure prone to cracking. "Look at this," Zhao said to his assistant, pointing to a Japanese transmission gear under the microscope. "See how the carbide distribution is uneven? That's why these gears fail under load. They're hard but brittle at the surface and too soft in the core." More troubling were the results of their chemical analysis. Using a portable spectrographic device provided by their American allies, Zhao's team determined that the Japanese armor plate contained significantly lower percentages of critical alloying elements compared to the German examples. Most notably, the German armor showed proper levels of molybdenum and nickel, while the Japanese steel relied primarily on carbon and manganese for its hardening. As night fell, Zhao sat by a small campfire, carefully recording his findings in a waterproof notebook. "The Japanese defeat was forged in their steel mills," he wrote, long before the first shot was fired. He couldn't know then how prophetic those words would prove to be, or that his analysis would eventually reach the desks of military planners in Washington, London, and Moscow. The next morning brought new orders. Zhao's team was to proceed to a recently captured Japanese research facility where documents on tank development had been discovered. As they packed their equipment and samples, Soviet T-34 tanks rolled past, their commanders calling out greetings in Russian. One of the Soviet officers, noticing their unusual equipment, stopped to investigate. "You are studying tanks?" the Soviet captain asked in broken English. When Zhao explained their mission, the Russian's eyes lit up with interest. "We have engineer officer who studies same things. Perhaps you meet him later." This chance encounter would lead to an unprecedented sharing of technical intelligence between Chinese, Soviet, and American experts in the war's final days, and reveal the full extent of Japan's metallurgical failures. The Japanese research facility, located in a camouflaged underground complex near Harbin, yielded a treasure trove of technical documents. Among them were detailed reports on Japan's attempts to replicate German transmission technology, along with metallurgical analyses of various tank components. Most valuable of all was a comprehensive report comparing the performance of Japanese steel alloys with samples of German armor provided through the country's technical exchange program. They knew, Zhao told his team as they translated and catalogued the documents, they knew their steel was inferior, but they couldn't fix the problem. The Japanese engineers had correctly identified their metallurgical shortcomings, but lacked the industrial capacity and raw materials to implement the necessary improvements. The documents revealed a desperate search for alternative alloying formulations that could match German performance using available materials, a search that had ultimately failed. With Soviet permission, Zhao's team transported their findings and samples to a better-equipped laboratory in the recently liberated city of Changchun. There, joined by Soviet and American technical experts, they conducted more thorough analyses that confirmed their field observations. The Japanese armor and transmission components showed systematic deficiencies in material composition, heat treatment, and manufacturing precision. Most damning of all were the Japanese Army's own test results, which showed that their best tank armor could be penetrated by American 75mm tank guns at ranges exceeding 1,000 meters, while German Tiger tank armor could withstand the same projectiles at half that distance. Similarly, Japanese transmission components showed an average service life less than one-third that of their German counterparts under identical test conditions. As the technical experts compared notes and findings, a complete picture of Japan's armored warfare failures began to emerge, a story of industrial limitations, resource shortages, and technical compromises that had doomed Japanese tanks to obsolescence from the moment they rolled off the assembly lines. And at the center of this story was the fateful decision Japanese engineers had made regarding the composition and treatment of their armor steel. The roots of Japan's metallurgical failures stretched back to the very beginning of their tank development program in the 1920s. Unlike Germany, which had a mature heavy industry and a long tradition of precision manufacturing, Japan had industrialized relatively recently. While Japanese industry had proven capable of producing world-class naval vessels, their experience with large-scale armored vehicle production was limited. The earliest Japanese tanks were based on foreign designs. In 1927, Japan purchased several Renault NC-1 tanks from France and a Vickers Medium C from Great Britain to use as the basis for their indigenous tank development. These early influences shaped Japanese tank philosophy, leading them toward lighter, more mobile designs rather than heavily armored behemoths. This approach made sense given Japan's strategic situation. Fighting primarily in China and Southeast Asia, Japanese forces navigated challenging terrain, including mountains, jungles, and rice paddies, where massive heavy tanks would have limited mobility. Moreover, their opponents in the 1930s and early 1940s generally lacked effective anti-tank capabilities, making lighter armor seem sufficient. However, the fundamental limitation facing Japanese tank designers wasn't tactical, but industrial. Japan simply lacked access to many of the strategic materials essential for high-quality armor production. Critical alloying elements like molybdenum, chromium, and nickel were in short supply, with much of what was available being prioritized for naval construction. This shortage forced Japanese engineers to rely more heavily on carbon and manganese in their steel formulations, elements that could provide hardness but at the cost of increased brittleness. The technical documents recovered from the Harbin facility revealed the extent of this compromise. Japanese metallurgists had conducted extensive tests comparing their domestic steel alloys with German samples. The results were sobering. Japanese armor plate with a Brinell hardness of 280 to 300 showed catastrophic cracking when struck by high-velocity projectiles, while German armor of similar hardness maintained its structural integrity under the same conditions. The difference lay in the microstructure of the steel. German armor utilized precise combinations of alloying elements and sophisticated heat treatment processes to create a fine-grained structure that was both hard and tough. Japanese armor, lacking these critical alloying elements, developed a coarser grain structure that was prone to crack propagation under impact. Faced with this metallurgical disadvantage, Japanese engineers attempted various workarounds. One approach was to use face-hardened armor with a very hard outer surface backed by softer, more ductile steel. While this technique was also used by other nations, the Japanese version suffered from poor bonding between the layers, leading to delamination when struck by enemy fire. Another compromise involved the thickness of the armor itself. Unable to match the quality of German armor, Japanese designers often compensated with thinner plates to reduce weight and improve mobility. The Type 97 Chiha medium tank, Japan's most widely produced tank of the war, had a maximum armor thickness of only 25 millimeters, less than half that of the American M4 Sherman, and less than a quarter of the German Tiger's frontal armor. These compromises extended to the tank's mechanical components as well, particularly the transmission systems. The documents recovered by Zhao's team included detailed analyses of transmission failures in various Japanese tank models. The pattern was consistent. Gears and shafts failed prematurely due to improper heat treatment and material deficiencies. One telling report described tests conducted in 1944 comparing a salvaged German transmission gear with a Japanese manufactured equivalent. Under identical stress tests, the German component withstood more than 3 times the load before showing signs of deformation. Microscopic examination revealed that the Japanese gear had an inconsistent hardness profile, with some sections too soft and others too brittle. This technical disadvantage had profound operational implications. Japanese tanks frequently suffered mechanical breakdowns, limiting their combat effectiveness and requiring extensive maintenance. Field reports from the Philippines campaign in 1944 noted that Japanese tank units typically operated at less than 70% of their nominal strength due to mechanical failures even before entering combat. The situation grew increasingly desperate as the war progressed. Allied naval blockades cut Japan off from imports of strategic materials, while American strategic bombing targeted key industrial facilities. By 1945, Japanese tank production had been reduced to a fraction of its already modest peak, and quality control issues had grown even more severe as experienced workers were drafted and replaced by inadequately trained personnel. What made these findings particularly poignant was the evidence that Japanese engineers fully understood the problems they faced. Technical reports from the Harbin facility included detailed analyses of armor failures and proposed solutions that could never be implemented due to resource limitations. One Japanese metallurgist had written, with remarkable frankness, "We know what must be done to match German armor quality, but we lack the means to do it." As Zhao compiled his comprehensive report on these findings, he couldn't help but reflect on the irony of Japan's situation. The nation that had launched a war largely to secure access to strategic resources had been defeated, in part because those very resources remained beyond their reach throughout the conflict. The technical gap between Japanese and Allied tanks had not narrowed but widened as the war progressed, culminating in the one-sided tank battles of the Manchurian campaign in August 1945. The clank of treads on packed earth filled the air as a column of Soviet IS-2 heavy tanks approached the Japanese defensive position. Inside the lead tank, Captain Dmitry Kovalev peered through his periscope at the enemy line, where several Type 97 Chiha tanks were positioned behind hastily constructed earthworks. He gave the order to halt at a range of 1,400 meters, well beyond the effective range of the Japanese 75mm guns, but comfortably within the reach of his own 122mm cannon. "Target the rightmost tank," Kovalev ordered his gunner. "High explosive." The massive gun boomed, sending a shell arcing toward the Japanese position. It struck just short of the targeted tank, showering it with earth and debris but causing no apparent damage. The gunner adjusted his aim and fired again. This time the shell struck directly, and the Japanese tank seemed to disintegrate, its turret torn away from the hull by the force of the internal explosion. The remaining Japanese tanks attempted to maneuver, seeking the cover of a nearby ridgeline, but they were too slow. Over the next 5 minutes, the Soviet tanks methodically destroyed them one by one, without a single Japanese round finding its mark on the Soviet armor. It was not a battle, but an execution, the culmination of years of diverging technological development. This scene, recreated from Soviet and Japanese battle reports, typified the armored engagements of the Manchurian campaign. The once proud Kwantung Army, stripped of its best units and equipment to feed other fronts, fielded obsolete tanks against the Red Army's latest models. But even at full strength, Japan's armored forces would have been outclassed by their Soviet counterparts. The technical intelligence gathered by Ming Zhao's team provided the explanation for this disparity. In his final report, completed in October 1945 and shared with Chinese, American, and Soviet authorities, Zhao outlined what he called the 3 fatal flaws of Japanese tank design. First was the fundamental material quality issue. Japanese armor steel, lacking critical alloying elements, was simultaneously too brittle and too soft. It shattered when struck by high-velocity projectiles rather than absorbing or deflecting the impact. This material deficiency could not be overcome by design improvements or tactical adjustments. It was, in Zhao's words, a foundational failure upon which everything else was built. Second was the inadequate manufacturing precision, particularly evident in transmission and drivetrain components. Japanese industry lacked the machine tools and quality control systems needed to produce consistently reliable mechanical parts for heavy vehicles. This resulted in frequent breakdowns that reduced operational availability and limited the effective range of Japanese armored units. Third was what Zhao called the failure of adaptation, Japan's inability to evolve their tank designs in response to battlefield experience. While both Germany and the Soviet Union dramatically improved their tanks throughout the war, Japanese designs remained largely static. The Type 97 Chiha that entered service in 1938 was still Japan's standard medium tank in 1945, with only minor modifications. These technical failures reflected broader strategic miscalculations. Japan had initiated a war against industrial powers whose production capacity dwarfed their own, while simultaneously fighting on terrain that often negated the potential advantages of armored warfare. Their decision to prioritize naval and air force development at the expense of the Army's mechanization made sense given Japan's island geography, but proved catastrophic once they faced the fully mechanized Allied armies. Zhao's analysis circulated among military planners and industrial experts in the immediate post-war period. It contributed to a reassessment of Japan's wartime industrial capabilities. The prevailing Western view of Japan as a technologically advanced nation was tempered by the recognition of significant gaps in their industrial development, particularly in metallurgy and precision manufacturing. For Zhao personally, the investigation brought both professional recognition and personal satisfaction. In December 1945, he was invited to Washington, D.C. to present his findings to American military and intelligence officials. His detailed analysis of material failures in Japanese equipment impressed the Americans, who offered him a position with their technical intelligence agency. Zhao declined, choosing instead to return to China to help rebuild its scientific infrastructure. The knowledge gained from examining both Japanese failures and German successes proved valuable in the post-war era. Metallurgical techniques pioneered by German engineers for tank armor were adapted for civilian applications, ranging from construction equipment to railroad components. Similarly, understanding the causes of Japanese transmission failures informed improvements in vehicle reliability across various industries. Perhaps the most profound legacy of Zhao's work was its influence on military procurement and industrial planning in post-war Asia. When the People's Republic of China began developing its own tank industry in the 1950s, planners explicitly referenced the Japanese experience as a cautionary tale about the dangers of proceeding without adequate industrial foundations. They ensured that metallurgical capabilities were developed in parallel with vehicle design, rather than attempting to build sophisticated weapons systems without the necessary material science expertise. The story of Japanese armor failures also influenced South Korea and Taiwan as they developed their own defense industries decades later. Both nations made significant investments in basic metallurgical research and precision manufacturing before attempting to produce advanced weapons systems, avoiding the fundamental errors that had doomed Japanese armored forces. Today, the tale of Lieutenant Ming Zhao's discovery is rarely mentioned in popular histories of World War II. Yet, for those who study the intersection of technology, industry, and warfare, it remains a powerful example of how battles can be won or lost in steel mills and research laboratories long before armies meet on the battlefield. The technical gap between Japanese and Allied tanks reflected not just different design philosophies, but fundamentally different industrial capabilities, a gap that no amount of courage or tactical skill could overcome. In his later years, having become a respected professor of material science, Zhao would often tell his students, the failure of Japanese armor was not just a military defeat, but a failure to understand the fundamental relationship between science and industrial capacity. It was a lesson learned at tremendous cost, one that continues to influence military planning and industrial development to this day. The rusted remains of Japanese tanks can still be found in remote areas of China, the Philippines, and other former battlefields of the Pacific War. To the casual observer, they are simply decaying relics of a conflict long past. But to those who understand the story revealed by Lieutenant Zhao's investigation, they tell a deeper tale of a nation that went to war with inadequate industrial foundations, whose tanks were doomed to fail before they ever left the factory. As we reflect on this little-known aspect of World War II, we are confronted with a profound truth about modern warfare. Victory is determined not just by the courage of soldiers or the brilliance of generals, but by the quality of steel and the precision of machines. The Japanese armored forces were defeated not primarily by enemy action, but by metallurgical failures that no tactical genius could overcome. Would you have recognized, as Lieutenant Zhao did, that the secret to Japan's defeat lay in the microscopic structure of its steel, that seemingly small differences in material composition and heat treatment could determine the outcome of battles and campaigns? This is the hidden reality of modern warfare, where victory often belongs not to the side with the bravest soldiers, but to the one with the best metallurgists, the most precise machine tools, and the most abundant resources. Comment below and share this story so others remember what courage really means. Not just the courage to face enemy fire, but the intellectual courage to look beyond the obvious and discover the true causes of victory and defeat in the modern age.